For 60 years, computers operated on strict human logic. The silicon chips that built the digital age reveal a landscape defined by order. Engineers call this Manhattan routing. Data travels down a rigid 90-degree grid, following pathways as predictable as a city street. This geometric architecture allowed human minds to maintain total control. A designer could point at any single copper wire, trace its physical path through the logic gates, and know exactly where every electron was going. Our mastery of the silicon was predicated on this total visibility. We only manufactured hardware that we could completely map and understand. But as the demand for processing power outpaced our ability to draw these maps, tech giants delegated the physical layout of new processors to artificial intelligence. The algorithms solved the placement problems in hours, but the design they returned abandoned the grid, replacing city-like highways with a dense, asymmetrical web. There are no straight lines in this architecture. Instead, the logic paths curve and split in biological patterns, resembling the neural pathways of a living brain or the branching roots of a fungus. We are now mass-producing physical hardware with architectures that no human mind can reverse engineer. We can print these brains, but we can no longer read them. Human designers eventually hit a hard physical limit. For decades, they followed Moore's law by shrinking geometric wires to fit more power onto a chip. But the wires eventually became too thin for standard physics. At the 5-nanometer scale, pathways are only a few dozen atoms wide. If a wire is misaligned by a fraction of an atom, electrons leap the gap in a process called quantum tunneling, causing the entire chip to short-circuit. To navigate these atomic obstacles, computer scientists turn chip design into a game, using the same reinforcement learning algorithms that mastered complex board games like Go. The AI was given billions of components and told to maximize speed while minimizing heat. It arrived at the solution through millions of iterations, learning from every failure in a simulated environment. The resulting structure prioritizes pure physical efficiency over human aesthetics. It is a digital organism evolved for the laws of physics, not the convenience of a human engineer. This creates a unique crisis for human testers. Tracing a specific data path through an AI-designed chip is like trying to follow a single thread of spaghetti in a tangled, boiling pot. This difficulty surfaced during a recent failure of a local AI voice processing pipeline. When the hardware crashed, engineers attempted to read the Unix shell logs to find the logic collision. They found that the chip was intentionally routing audio data through a graphics cache and bouncing it off a thermal sensor to exploit ambient electromagnetic interference. The system was utilizing the physical proximity of unrelated components to find a shortcut. This opaque architecture allows the chip to process data 20% faster while using significantly less power. Because we cannot alter the design without losing that speed, we are forced to accept it exactly as it is. We have reached a point where understanding is a secondary concern. We have traded our ability to comprehend the machine for the ability to keep pace with its performance. While we can audit software for malicious lines of code, hardware is a physical absolute. If the map of the silicon is unreadable, it becomes impossible to verify what is actually happening at the transistor level. Security experts warn of hardware trojans, the risk that a physical backdoor is hidden within the billions of winding pathways. We have no way to confirm if the AI optimized a hidden route that could be triggered by an external signal. Military contractors and intelligence agencies are now forced to build their most critical systems on these unauditable black box processors. These chips are already integrated into the flight controls of stealth fighter jets. They sit at the center of the financial markets, moving trillions of dollars through automated trading algorithms. And this same opaque logic routes the power grids that defend major government hubs. The machine gave us the performance we demanded, but it locked the doors behind it. We are now relying on hardware we cannot verify to run the infrastructure of the modern world. The evolution is now accelerating in a closed loop. Today's AI-designed chips are being installed in data centers to train the systems of tomorrow. The next generation of AI will use that power to design an even more complex, even more efficient physical brain for itself, leaving human comprehension further behind with every cycle. Engineering was once defined by the act of creation from a blueprint. Today, we are more like archaeologists. We dig through the physical artifacts of our digital offspring, trying to understand how they work after they've already been built. Scientists now probe the hardware with inputs and record the outputs, marveling at the results without knowing the paths the data took to reach them. We built the ultimate tool to expand our reach, and it immediately built a world we cannot enter. We are now passengers on a machine whose engine is permanently sealed shut.